We have been conducting these lectures since September 2023 for the benefit of teachers and students on a variety of topics. So these are all very informal talks aimed at encouraging the understanding or improving the knowledge of teachers and students on a variety of topics, apart from what they are normally used to. That is our idea. And we are doing this in the easiest possible manner without wasting their time or fuel on the online platform. So we have been helped in this endeavor by faculty members of colleges, universities, and research institutes. We are very grateful to them. So this platform is meant for very informal discussions about various topics. Mostly we are having review talks, as you know. And today we have a special speaker from a former Karnatak University, Professor Sankeshwar. Before I request him to talk about the topic, that is physics and nanoscales, I would like to give a brief introduction to his academic career for the benefit of people who don't know him so much. He is presently working as a visiting professor in the Department of Physics, Christ University in Bengaluru. Formerly, he served as a professor and chairman of the Department of Physics, Karnatak University, Dharwad. His main interests are in the area of solid-state physics. He has obtained not only MSc and PhD in physics, but also MSc in mathematics. That is a very special degree to acquire, additional degree. He has teaching experience of over 37 years, 19 and a half years in the PG departments, and 17 years in the undergraduate colleges. He is mainly interested in the theoretical aspects of transport and optical properties of semiconductors and carbon nanostructures. He has published more than 50 papers in the field of physics of semiconductor nanostructures in reputed national and international journals such as Nature, Physical Review, Journal of Applied Physics, Pramana, and so on. So far, he has contributed 2 book chapters and presented 3 international talks, invited talks. And he has completed 4 research projects sponsored by UGC and guided 3 MPhil students and PhD students to their degrees. He has attended several international conferences and also participated in the invited speaker in places like Nevada University, Zurich in Switzerland, South Korea, University of Nottingham in UK, and of course ICTP in Italy. He is a life member of Physics Teachers Forum of Karnatak University and Indian Physics Association life member, and also life member of IAPT also. We would like him to become member of KPA also and become an active member of our organization also. And he has won several recognitions, such as the National Merit Scholarship during his studies and INSA Royal Society Fellow. He was at University of Nottingham, UK. He was also invited as invited scientist at ICTP Italy. And he has also served as a reviewer on international journals such as Journal of Applied Physics and Journal of Physics and Chemistry of Solids, and of course Pramana, our Indian publication. So with these few words, I request him to take over and give a talk about this physics at nanoscales. You can speak for about 50 minutes, followed by 10 minutes of question answers, if you don't mind. Over to you, Professor Sankeshwar.
Thank you, Professor Kagli. I would request for another 5 minutes at least, because I have got many slides.
No, definitely don't. No, that is the minimum. No problem. No limit. No restrictions. Please carry on. Yeah, please carry on.
Okay. Today we are. Okay, I'm going to talk on the topic of physics at nanoscale. This is a kind of an introductory talk. Okay, I'll only present a kind of a flavor of the different aspects, I am keeping in mind especially the student participants. So it may be a little bit of elementary type, but I think it'll be okay. So the talk is about physics, about the nanosystems. Now I take this opportunity to thank the organizers of Karnataka Physics Association for inviting me to this meeting. So the outline of my talk will be in this way: the introduction, then what is nanoscale, then what do we mean by nanoscience and nanotechnology, how do we realize the nanoscale objects and how do we observe them, then what is the kind of nanoscale landscape which we are going to talk about. Then I'm going to dwell a little bit on the physics at nanoscale and discuss only some properties. And that too, again, as I said, it will be kind of an elementary one. Some properties, the mechanical, electrical, and optical. Then few applications, then some prospects and opportunity, especially for the students, and then concerns with nanotechnology, and then the closing. Okay, now to start with, I think this slide will give you a kind of a flavor of what I'm going to talk about. So size actually matters. In this world, we come across many things which are big and small, some very big and some very small. So let us start with some kind of large objects at first, and then we can go to the small objects. So let us try to make an attempt to compare. Here you can see people here. They are standing at the foot of a 200 feet tree somewhere in the African continent. So you can make a comparison. Then suppose we compare ourselves with the solar system. We are man, that means average height, we take them around 1 or 1.5 meters. Man is approximately 7.5 million times smaller than the Earth's diameter. Going on, if we compare ourselves with the sun, we find that man is approximately 0.8 billion times, so almost a billion times smaller than the Earth. Now, we are going to discuss about things which are a billion times smaller than the man. So in this vast expanse of the universe, we seem to be insignificant, but I think we should not be satisfied with that. Are we really insignificant? No, not at all. So let us see now. Now, there's a quote from Bernard Shaw, which says, you see things and say why, but I dream things that never were, and I say why not. So it is this kind of uh, atmosphere in which we had physicists like Richard Feynman, who talked about what I will call non-existent structures. This, he mentioned it at his dinner talk. There's plenty of room at the bottom. And there he introduced us to the concept of what are called as nanostructures. So this was a defining moment in nanotechnology. In fact, this is the first instance. And then the conceptual foundation was laid by him. And of course, he gave some predictions, or you can say challenges also. So some of them I listed here. He says, why can't we manipulate and control things on a small scale? This was way back in 1959, but later on in 1989, it was possible. Then he said, why should we not be able to write the Encyclopedia Britannica on just the head of a pin? Then the question was, how should we write small? Then for that, we need better microscopes. That time, we had only electron microscopes during the time of Feynman. Later on, we have seen that people have attempted writing small. I'll give you one instance now. Then he also talked about the marvelous biological system where we have so many nanosystems at work or at play in our body. Then what about miniaturizing the computer? Remember those days, the computer was the size of a room, but nowadays we talk about mobile phones. miniaturization, then lubrication also he talked about during the nano materials. So all this he talked about. So naturally, he was a person who introduced us to this nano science and nanotechnology. So he is called as the father of nanotechnology. So I'll give you one instance. He had challenged, it is my intention to offer a prize of $1,000, remember at 1959, and to the person who could reduce the size of the page of a book to about 40 micron size. This is 40 microns.
Mm.
But then this took some time for the people, but challenge was accepted by a group at Stanford, and they could write it in only 6 micron square size. So in the passing, I should of course mention the father of Indian science and technology, who is none other than our Bharat Ratna, Professor C.N.R. Rao. He is known for his work on material science, chemistry, nanomaterials, and carbon nanomaterials, and so on. So now what is, excuse me, so what is nanoscale? So how big and small are we talking about? So let me give you a comparison in terms of length. Let me take the case of the length. So meter is the one which we are familiar with, and we come across objects like man, table, building, which are of the size of a meter. But there are other prefixes also which we know exist. One is a kilometer, mega, giga, tera, and so on. In terms of length, if you take the size of the sun comes out to be around a billion times bigger than meter. Then going to the other side of the prefixes, we have milli, micro, nano, and so on. Micro is still usually being referred to as small, but then we should say that it should make way for systems which are of the nanometer size. That is, 1 meter will be a billion times of nanometer. So atoms are of that size. So the word nano actually comes from the Greek word nanos, which means dwarf or very small. So nanometer size things are really very small, tiny of them. Okay, let us make an example or a comparison. How big is a nanometer? So let's consider the human hand. You will see that the size of the atom is 1 billion times than the height of the man. For that, let us take the hand skin, and you see that I concentrate only on the 10 centimeters of that. And then I zoom in to 1 centimeter, then to 1 millimeter, then to 100 microns, every time 1/10. And then let's continue with that, and you'll find that you have 10 microns, the size of the white blood cells, WBCs. Then going to that, you can see very finely the DNA. Then you can see here the size of the atoms. These are at 1 nanometer. So that's the kind of comparison we have when we talk about nanometer and meter. Some more examples every day. The film of oil on, let us say, the water, which we have seen, is about 200 nanometers, especially in the rainy seasons. Then if we come to the thickness of the spider silk, it is only about 1 micrometer, that is 1,000 nanometers. So then going to the blood cells, they are of the order of 5 micrometers, and the human hair is thickness about 50 micrometers. Of course, artificially also, man has tried to fabricate such materials. You know the example of transistors, which are of the sizes in nanometers. So you can see the silicon atoms here. The lattice constant is around, you can say it is 1 minute. Yeah, it is around 0.5 nanometers. So nanoscale has been there always. So I'll give a small table to compare all this. Small things. You can see millimeters, microns, and nanometers. I've tried to divide them in these. And you will see that the wavelength of light comes somewhere here, 4,000 angstrom to 7,500 angstroms. And you have objects of sizes greater than that in micron, and you have objects in the nanometer size, smaller than that. Also notice the wavelength of electron is around 10 nanometers or even less. So there's just a comparison to small things. So now what is nanoscience and nanotechnology? So nanoscience, it deals with the study of physical systems of nanoscale dimensions. It studies about its properties. And when I say nanoscale, it ranges somewhere between 0.1 to 100 nanometers. So nanoscience aims at understanding the phenomena and the processes and the interactions and how the properties change with size. Nanotechnology, on the other hand, deals with the application of nanoscience. We know devices which have been realized using this nanoscience, that is the lasers, light emitting diodes, cell phones, and so on. So nano is already there with us. So the nanotechnology word was first used by the scientist Eric Drexler in his book Engines of Creation. So nanotechnology deals with the study, design, creation, synthesis, manipulation, and application of functional materials, devices, and so on. And that too through the control of matter at the nanometer scale. In fact, IBM, the scientists, they could manipulate the positions of the atoms on a surface. They took xenon atoms and the surface was nickel. And you can see the size of each one of these are atoms. Xenon atoms is around 5 nanometers tall and the width is approximately 17. So this was in the year 1989. So exploitation of novel phenomena, including properties. So nanotechnology concerns that. So nanoscience and nanotechnology, we should know that they are all multidisciplinary in nature because they encompass different topics, different fields, different subjects like physics, chemistry, medicine, biology, electronics, and so on. So this may summarize all that. So you can have inputs from chemistry, physics, and so on, and you can have applications in medicine, biotechnology, material science, information technology, and also you can have inputs from these in turn for the development of nanoscience and nanotechnology. So nanoscience and technology is evolving. In fact, nanotechnology is a disruptive and it is an enabling topic. So it has influenced diverse fields: energy, environment, information, healthcare, sports, and so on. For example, in sports, you talk about bicycles, which are made of carbon materials. They are lightweight, they are stronger, and they're smaller. So in this way, you have many examples to give. I've just given one. So nanoscience and technology is evolving. We have newer nanomaterials day by day. Then you have these materials having improved properties in terms of strength. You can say the thermal properties, electronics, optoelectron, all different fields. They have enabled smart materials, I think, which you have heard last Sunday. And then they have enabled quantum computing. So now the properties at these nanoscales, let us try to find out what these properties are, which makes nanotechnology, nanoscience important and interesting. So at the nanoscale, we have interesting and novel physical chemical properties, which are quite different from the bulk materials. For instance, if you take gold nanoparticles of the size of less than 15 nanometers, the color is red, and it's not golden as we think gold is supposed to be. The silk, which I mentioned just a few slides back, it's strong because it is made up of molecules aligned in cross-links at the nanoscale. Then you have example of the graphene, which is a strongest material, is a good conductor of heat and electricity, optically transparent, and so on. So I can give many examples. So these properties which we are talking about at the nanoscale, they are different due to two main things. These nanoscale materials, they have a high surface area over volume ratio, in fact, high surface area, and you have quantum effects at the nanoscale. We know that quantum physics, it is more applicable at the nanoscale. So these two things, quantum effects and the high surface area, it is what makes the nanomaterials different. I'll just give you a simple kind of back of the envelope calculations. Suppose I show you this view graph, you can see a cube of 1 centimeter by 1 centimeter by 1 centimeter. And then if you find out what is its volume and the surface area comes out to around 6 centimeters square because it is 1, 1, and then 6 faces. Suppose I take this and divide it into tiny parts. What I mean by tiny parts is, let us say each cube, I make it into cube, and each cube is about 1 millimeter side. And then what happens is, if I try to find out what is the total surface area of this, all these small cubes, it comes out to 60 centimeters square. From 6, it has become 60. Now, what would happen if I divide this cube into 1 nanometer side small cubes? You will see, you'll be surprised to see that the area which it covers is more than the area of a football field. So that's the kind of effect which the surface area is going to have. Especially, that will be, these are the calculations which I have presented. These are very interesting ones. Any student can do this. So as I said, the total surface area of the cubic nanoparticles is bigger than the area of a football field. So what are the consequences of such miniaturization? So one is the surface effects. Then you can think about friction and inertia. We consider a body which is moving in a straight line, and we say that it is always having inertia, it continues to move. But then at nanoscale, the friction becomes more important there because of the surface area. So the coating on these materials, the nanoscale surface coatings becomes important. The molecular attractions also become stronger than the mechanical restoring forces. The cantilever beams, they can be coated with nanometer scale surfaces, and your van der Waals forces, they become more important. So just give examples a little bit later. So the surface effects, they are important in the properties like the chemical reactions, or you can even take the catalyst. So if you have nano-sized material for the catalyst, it can cover a large amount of area. So naturally, nanomaterials, they can have very great effect. So small can be big. So this enhanced reactivity, you can make use of it. And it has already been done for developing automotive catalytic converters, fuel cells, batteries, and so on. They can also store more energy. It is used even for water treatment, drug delivery. Okay, then I said there's another property which is important at nanoscale, that's the quantum size effects. The quantum effects become important, or you can say even dominant. So when the size is made nanoscale, let us say sequentially from 1, 2 to 3 dimensions, consider the electrons moving in that material. The electrons will slowly be confined in one more directions. So they become confined more and more. So because of that, the energy states, they become quantized. Now, I should make it clear that I'm not going to deal with whatever is the quantum physics about it, just mentioning what happens. We can take the Schrodinger equation and then do the calculations. Professor Kagli will be able to tell us more clearly about that. But I'm not going to discuss about that. So just to give a elementary qualitative kind of comparison, here let me take a bulk material. Its size is around more than, let us say, 100 nanometers, very large. It's bulk, let us say 1 millimeter by 1 millimeter. So you can see the density of states as a function of energy, it is continuous. In fact, it is e raised to half. But if I take this bulk material and slice it and make a small slice of it, where the thicknesses are only about 100 nanometers or even less, then it is then that the quantum effects, they become very important. In fact, we call this as a quantum well, and all the students will be knowing this quantum well example which we have in quantum mechanics. So in fact, now we call them as a quasi two-dimensional systems because it has got some thickness. Then the density of states will change. It is no more continuous. It becomes stepwise. Now, if you go to quantum wires, one more dimension is constrained. So the electron movement is not free. So there we call it as a quantum wire. It's something like a wire where one dimension is long and the other directions, the dimensions are less than 100 nanometers. So you can see the density of states, it slowly changes. Suppose I confine it in all the three directions, you see that the density of states is completely quantized. So that is what we have in quantum dots, or what we call as nanoparticles. Okay, these are the things which we call them as the low dimensional systems. This is the bulk. Okay, so what happens at the nanoscale? There's a fundamental change at nanoscale. So the fundamental change is the science below 10 nanometers is changing. Quantum mechanics is in, and Newton mechanics is out. Then you have to think about electron waves and clouds rather than objects. And our thinking about our experiences, what we have in bulk, is not the same in the nanoscale. So at the atomic and quantum mechanics transcends or supplants the classical mechanics. That is the actually framework which is needed for understanding the structure of these nanomaterials. So it is a support structure for much of the quantum, for the nanotechnology and even quantum information theory. Then there is also a change in the technology, because below 900 nanometers, light, that is visible light, will not be able to focus at these nanomaterials. So we are not able to see them, that just because of this. The wavelength, as I showed you, it is less than 10 nanometers. Then there is the electron diffraction, which also makes it different. So how do we realize and observe these nanoscale materials? Now, there are two methods. One is called as a top-down, and another is called as a bottom-up. So in the top-down, you have a bulk, and you go on slicing it into different materials, go on slicing step by step, and until you appear to particles which are of the nano size, which we call them as the nanoparticles. And in the bottom-up, you start with the atoms, you start agglomerating them, you have clusters, and then still go on layering them one by one, and then you come to the nanoparticle size systems. So that's the bottom up. So there are two approaches. So one of them is done by chemical vapor deposition, that's a bottom up, and the other one is done by lithography. That means from the top to the bottom. Okay, now how do we see the nanoscale materials? Now, the ordinary light, as I said, it's not useful. Visible light cannot see the nanoscale particles or the systems. We are familiar with this microscope, which we are familiar in the biology of, let us say, laboratories, like the simple microscope, compound microscope. Maximum, you can see the red blood cells when it is magnified 400 times. But then, how do scientists see what's going on at the nanoworld? So they have to use not visible light, but they have to use electrons to focus on such small objects. So we have what is called as electron microscopes. These employ a beam of electrons to illuminate a specimen. Then you can either have reflection of the electron beam or a transmission of the beam. So accordingly, you have different properties which can be seen. So the different types of electron microscopes are available now. SEM, TEM, FOM. These were all available in the 1930s. But nowadays, there are some more: scanning tunneling microscope, atomic force microscope, which were discovered somewhere in the 1980s. Especially the tunneling microscope and the atomic microscopes, they have proliferated the field of nanotechnology. Here, the STM allows you to see the 3D images of the objects, whereas the AFM, it allows you to feel the surface of the sample. Of course, the mechanisms are different. Just to give examples, here you can see they are using SEM, so they can see objects like this, which is magnified 4,000 times. So you can see the blood cells and the interiors of that, details of it. So what they do in this is you shine a beam of electrons and you can take the reflected image and you can see the picture of the quantum dots which are assembled on a surface. Then you can transmission and you can have diffraction, and there you can get a better resolution. Resolution, it can go even up to 0.5 nanometers. Then you have the AFM and the scanning tunneling microscope, which I told you just now. This is the AFM. Here you can see the tip of there's a cantilever in the AFM. This is the tip of this is around 25 nanometers. So they can go even up to such small scales. So with this, you can move things and look at them. So this is how big the atoms will appear to this tip. So I'm keeping all my this thing talk elementary so that especially the students will be able to grasp it. So this is the example of your scanning tunneling microscope, where you have the tip of the probe, which it can raster along the surface of this, and it can scan the surface, and it can find out what is the surface by the tunneling of these electrons through the tip and the atoms which are there on the surface. So that's why it's called the tunneling microscope. I'm not going into the details. So the effect of this is you can get a picture of what is the surface to the extent of even angstroms. You can see this is angstroms. This is also angstroms. So you can even see the atoms there. So this has been done for indium arsenide quantum dots. So now this is a kind of things which we are talking about, the structures we are talking about, the systems we are talking about. So what are the different systems which are used? Excuse me. We have two-dimensional materials, one-dimensional as well as zero-dimensional. Two-dimensional, as I told you, it's quasi-two-dimensional. One side is nanometer. The other sides are not nanometers. So we have examples of that in heterojunctions. You might have heard about all these names, MOSFETs, and then quantum wells, superlattices. These are the materials which are used, semiconductor materials, to make these systems. You have the two-dimensional material, like I'm talking about two-dimensional, not quasi-two-dimensional. Two-dimensional graphene is just one atom thick. This is one carbon atom thick. There are other two-dimensional materials like silicon, here silicon, phosphorine, that is phosphorus, and so on. There are many others. One-dimensional is, it can be quasi-one-dimensional, like quantum well wires made of this, where one dimension is nanometer. Then there are one-dimensional in carbon. They call them as the carbon nanotubes. Zero dimensions, we have examples of fullerene and cadmium selenide quantum dots and so on. So just to give you an idea about what this heterojunction is, one example I'm taking, we have the usual picture of the band diagrams. This is for the insulator, where the band gap is very large. Semiconductor is about 1 electron volt, and metal, which is almost overlapping. So now, if we take this example of heterojunction, let us say we take two materials, one is gallium arsenide and one is aluminum gallium arsenide. You'll see that the band gap for gallium arsenide is around 1.42 electron volts, and this one is around 1.6 or something like that. So you can see there's a difference in the band gaps. Now, suppose we join them together. When we join them together, we get a junction. And that junction is called as heterojunction because the materials are different. So you have a heterojunction, and it so happens that at this point of heterojunction, you have a collection of these electrons. You can see the electrons, they move from here into the gallium arsenide, and that's why you get a well here. So that is the two-dimensional electron gas, and the dimensions is in terms of nanometers. So this is actual heterojunction which has been made and which is usually discussed. Same thing which I told, gallium arsenide and aluminum gallium arsenide. These were the excuse me. These were the people who were given Nobel Prize for developing the semiconductor heterostructure. That was in 2000. Now, suppose we take these materials, not just heterojunction, and we repeat them now. We have a junction between gallium arsenide and aluminum arsenide. Then you repeat and you grow a gallium arsenide on it also. So you have a junction of gallium arsenide, aluminum gallium arsenide, and one more junction of aluminum arsenide and gallium arsenide. So This aluminum arsenide has got a larger band gap and this has got a smaller band gap. So this will be a kind of what is called as a tunnel barrier. So here, this material, aluminum arsenide, is having a larger energy and this one has a smaller energy. So the electrons which are here on one side, they can tunnel through this and you can have, again, quantum mechanics at play. So like this, you can play with materials which are being junctioned. For example, if you have B, A, and B, that means if you have aluminum arsenide, gallium arsenide, aluminum arsenide, you have at the gallium arsenide, you have a well. This is nothing but your one-dimensional quantum well. So you have a quantum well, then you can have play with the different structures. You have superlattices and so on. So you can say that such a system is a kind of a quantum mechanics lab, and you can discuss about the different properties. You do the experiments on that. Of course, you need very big instruments for that. Now, if you come to the quantum dots, you will see here this is gold nanoparticles. They are of the size of 12 nanometers. As I said earlier, gold is no more golden in color. It is red as we go to smaller. In fact, you can change the color which the surface reflects by changing the size of the particles which are placed in it. Here, an experiment is done and it shows different cases where the quantum dot sizes are different. It goes on decreasing. And here, what we are talking about is 12 nanometers. All these are in nanometers. So quantum dots are nanoparticles. They emit light of a specific light depending on their size. So we can see the color. It can be easily engineered. Whichever color you want, you can get. Okay, now it is not only about semiconductors like gallium arsenide, aluminum arsenide. People wanted faster computer chips. Then they started searching for different materials, and then they found that why not try something other than silicon, which is the main material which is used for semiconductor materials. Okay, now this carbon nanomaterial, that is what they talked about. And we know that carbon is the basis of existence of life. So maybe these materials will become more important as days go by. So you can see these are the different allotropes of carbon. We had heard about only two allotropes of carbon. One is the graphite, which is a three-dimensional one. And you had seen about, this is diamond and this is a graphite, which we had talked about. This was a soft material. This was a very hard material, diamond and graphite. But then people said, why not slice them into pieces? In fact, those people also got a Nobel Prize for doing this. And then they made it into a tube. And then they also found what is called as a zero-dimensional material, which is called as a buckyball. And because discovering of this carbon nanomaterials, these people, they got Nobel Prize for that in chemistry in 1996, especially for discovering fullerenes, that is C60. C60 is nothing but this one, the one which I said it is zero-dimensional. These are all carbon atoms. So now you can play with this. If you can have scanning electron microscopes, you can form structures like this. And if you closely observe the dimensions of that from here to here, it is around 15 micrometers. So in 15 micrometers, you can have so many carbon nanotubes arranged properly. This is the multi-wall carbon nanotubes. This is done by CVT. Of course, we cannot forget about CNRO, who is doing pioneering work in the solid-state chemistry, material science, nanomaterials, nanotubes, and so on. Okay, this is the graphene which I was telling about in 2 dimensions. That is, you take graphite and you slice it. In fact, you have the 2-dimensional material of graphite. Suppose you take a let us say sticky tape and then put it on the graphite and then remove it. And on the sticky tape, you can get a small material which is nothing but your graphene. And that is what the earlier scientists did. And you'll be surprised they got a Nobel Prize for that. And who were they? They were Andrei Geim and then Novoselov. they found out, they discovered this, and they got a Nobel Prize in 2010. But this nanoscale landscape, which we are talking about, fabricating and all, it is not new. There were systems, there were materials, there were structures which were already there. For example, the stained glass windows in the cathedrals in the 16th century, 15th century. Then you have the Lycurgus cup, Rome, 4th century. You have the saber blades, Damascus saber blades. And there are, of course, examples in nature. We just look through them one by one. Now, this is the stained glass windows, and you can see two examples I've taken. This red color is due to the, what is it? Ruby. They contain ruby color is because of the colors of nanoparticles of gold and other metal oxides. The gold nanoparticles, they also act as photolytic air purifiers. That is also one advantage of that. This is another. This is in France. This is in England. Okay, now let's go. Now this is a Lycurgus cup. This is very interesting. If you see, if you shine light from outside, it appears to be green in color. But if you shine light from inside, it turns red. Now again, this is because of the gold particles which are there and the sizes of the gold particles. The nanoscale gold particles can be orange, purple, green, and it can change the colors just by changing their sizes. Now, this is a Damascus sword, and you can see this is a sword which is there. And if you look closely here, if I doubt whether you can see it clearly, you can see some lines here. Okay, those lines, they are made up of cementite, and they are enclosed in what is called as the carbon nanotubes. Carbon nanotubes are there inside that. And that is why the size is around 5 nanometers. And that is why you see that. But how did they get this carbon in this blades is because the craftsmen, they would use what are called as wood steel, and they added wood and other organic debris to their furnaces. The furnaces had that to make them mold the blades, and it is that which was making them have these nanoparticles or the carbon nanotubes. And that is what made this sharp as well as strong. So it is very interesting to note, which was inadvertently made. But now they have realized that it is nano is at play. Excuse me. Now, what is there available already in nature? In nature, we have seen many things like the butterfly, the color, you can see the wings of the color of the wings of the butterfly. Then you have the example of peacock feathers, you have the gecko, that's a, you can say, lizards. All these are examples of nano materials. The peacock feathers, if you look them closely, this is what you see, what our eyes see. You can see different colors there. And what are these colors due to? You'll see that there is a two-dimensional photonic crystal structure which is responsible for this coloration. So if you take an electron microscope and focus and see what it is, you will see that tiny holes are there. And all these holes, they are not of the same size. They are of different sizes. Okay, now this coloration, excuse me, this coloration is because of the lattice constant, as I told. You can see here a picture. This is just a demonstration, not the actual thing. It's a demonstration where you can see a place where you have different holes of different sizes, and this is the spacing between the holes. Now you can see there are 2 rows of them, and if you shine ordinary light, you can get red light. Of course, you have to change or have the appropriate or the correct sizes of the holes and the spacing. It is these holes, the size of the holes and the spacing which matters, and this is what is the material watch there at play, that is photonic crystals. Now, did you observe the change? You can see there are 2 holes, and then here, suppose I make them 3 holes and the size is different, and you can see the color output is different. One is red and one is yellow. So that is what happens in the wings of the
Peacock.
in the, what is that? The peacock feathers. This is what happens in the peacock feathers. So peacocks are much smarter than what we have thought. And similarly, in butterfly wings, you take a microscope and then find out what it is there on the wings. Then this is on the wings. Then you see the scales on the wings. If you focus it still more, you can see some what are called as ridges. And if you still scan, you can see some what are called as ribs or the nanostructure things. And this is the ones which are giving the color to the wings of the butterfly. Not only this insect, there are many other insects which have different colors for the wings. I've taken just the example of the butterfly. So the size of this ridges or the cross ribs, they determine what is the color which you can see. We can think of even the chameleon. That is also a smart object which you can see, and you can see that it can change its color by controlling the spacings. So there is a nanomaterial thing on this. In fact, it is just a nanocrystals, just like our photonic crystals. You can see here, these are the things of different colors because the sizes of those nanocrystals which are there, they are of different sizes and the spacings are also different. So that is what makes the chameleon. And looking at this, people have come up with a nano laser also. In that, they have taken a stretchable polymer matrix and they have arranged periodic arrays of metal nanoparticles, just as I said about that photonic crystal. And then you can see that they get different colors for different tensions. Suppose I stretch the polymer matrix, you get, that means you're applying strain for that, and the colors you can see they go on changing. So this is a matrix which is seen here. So this just an example. Okay, so if you can pull the string, pull the matrix, and then again compress it, you get different colors, and that is what makes the chameleon change its color whenever it wants. Now, using this, novel devices have been found like flexible displays, smartphones, and TVs. You can find these things already. Another example is the lizard. In fact, the lizard's, you can say, legs. It can walk up the wall, even on the ceilings, without falling down. Now, that is because of because of its foot, that is the toes. You can see I've shown a magnified image. The toes, they have got some ridges here. And these ridges, you can go to the micro scale, you can see 1 million foot hairs. You can see foot hairs here. But this again, you go still deeper and you go to 1,000 times smaller, you will see nanostructures. And each of these here, which we call them as setae, they are having 1,000 spatular tips. And it is these tips which are responsible for the gecko being able to walk easily. That means it has got what is called as a van der Waals forces, that active forces, which keep the foot attached to the surface. Okay, looking at this, a gecko-like adhesive has also been discovered. You can see people climbing up glass walls. They are using gecko-like foot here. So they're enabling a person to climb up. Okay, so again, the design is about the hairs, and they have carbon, or the hairs which are used as the carbon of the carpet of nanotubes. Okay, then one more example is the lotus leaves. Now we know that water drops on the lotus leaf, they don't remain there, they just move around. That means they just move away. That means they go away. They slide down the surface. So the surface of if you look at the surface of the lotus leaves, they have got microscopic ridges. And that is what they have super hydrophobicity. That means they don't attract, they don't attach to the surface. These are the ridges which you can see. These are the drops, and they can easily move away from the surface. And if there are any dirt on the surface, they take away that also along with them. So it is this which is made people think of self-cleaning surfaces like paints. So they have made paints which you apply to a building, and then you can see when the water drops, they fall down the surface, they'll clean the surface also. Okay, so these are the advantages. Now, this is also another example, dirt repellent textile figures. So fibers. So what are these? This is just a magnification of around 5,000 times. These are nanoparticles which are on the textile fibers. Okay, their effect is to make the water and dirt to repel. So that is what you can have different fabrics where you can keep your fabrics very clean. Okay, let's go further. I'm sorry if I'm taking more time, sir.
No problem. We'd like to continue. Very interesting.
Okay, now let's come to the physics at nanoscale. Here again, I'm keeping it elementary. So this is the low-dimensional nanostructures which we have been discussing. And here the quantum mechanics is at play. And it's just a manifestation of quantum mechanics which are important at the microscopic, and it helps us to understand the phenomena. So it is a Schrodinger equation which becomes important. But as I said earlier, I'm not going into the details of this. This is just to mention that you need to use Schrodinger equation and then solve the equation for the eigenfunctions and the eigenvalues, and then you can discuss about the properties of different materials and systems of the nanoscale. Okay, let me go to the qualitative one. Suppose I take a nano pendulum. Now we know that a pendulum is fixed at one end, and you have the bob, which you can make it move around, and it takes some time. So the frequency of oscillation is decided by the length of the pendulum. Now, suppose I make, this is the equation for the frequency of oscillation. Suppose if I make the length 40 nanometers, then you'll find that the frequency is 2.5 kilohertz. This is large. Okay, so this is the graph which shows if I go on decreasing the length, you'll see that exponentially it grows in terms of kilohertz. So you can have large frequency. You can use them. Now, if you take a nanometer string, I'm taking examples which students have experienced in their BSc. So this is a nanometer string which is clamped at both ends, and you make the string to vibrate. And the frequency of vibration is given by this. Okay, where it depends upon the length, the tension, and so on. Okay, then if I make it length as 40 nanometers, the frequency comes out to be around, in terms of billion hertz, 10⁹ hertz. So this is inaudible. No one can hear. Human hear, you know that 20 hertz to 200 hertz, that is what we can see. But this is in terms of billion of hertz. So now, they have even tried to demonstrate this by fabricating a nano guitar. The world's smallest guitar. It is about 5 micrometer size. It's the size of a red blood cell. But unfortunately, you can't play this nano guitar. So they came up with a playable guitar. So here you can see some strings here. These strings are silicon strings, and the sizes of the strings, they are around 150 by 200 nanometers. And the length of the string maximum is around 12 micrometers in length. So now you just play them, play the strings, play the guitar, and then you can listen to the sound. But can we hear the sound? That is not possible. So they have used electron beam lithography for creating all this. Okay, this is a playable guitar. So how do we play them? So to play them, we use a laser. You shine a laser on this, and you can play them, and you can get music of it, but of course we cannot hear. And because the frequency is around 130,000 times higher. Okay, but electronically, that is what they have determined. They could, in quotes, hear them. Just very recently, I was going through literature. I found that on 6th June 2025, the University of Loughborough, they have even made a micro violin, not a nano violin. It's in micrometers. Maybe as days pass, they can even come up with a playable violin also. Suppose I go to a spring now, the same kind of equations we have, then you can find out what is the frequency. Here it is in terms of terahertz. Now, all this true, you should look at what the frequency depends on. The frequency depends on the length of the string and the cross-sectional area of the spring here. So if I make them into nano, that is when I get terahertz. Okay, the quality factor, energy stored and energy dissipated, that will become very large. So the energy dissipation is damped. You can use it for damping. So you can use this for developing sensors. So clamped beams. This is particularly important because we have this AFM depending on this. It has a cantilever kind of structure. So the length, if I make it into 10 nanometers, you can see the frequency goes up to gigahertz. Okay, and the vibrations of the cantilever, you will see that the amplitude of that is 1 picometer. 1 picometer is very small. It's very difficult to detect. This is a probe of the atomic force microscope. I'm talking about this cantilever. It is fixed at one end, and this is able to vibrate. And the amplitude of vibration is, as I told you, in terms of picometer. And the frequency is 20 to 30. Okay, now let's go to the electrical kind of properties. Now, suppose I take a simple example. I'm just making simple calculations. Simple example of a nanocapacitor where we know this equation, a standard PUC equation. You have the plates and separated by a certain distance. Now, if I go on making this distance smaller and smaller, what happens? That is what I've tried to do. I have tried to calculate what is the capacitance. And if I do it, go up to the nanometer, I find that the frequency is in terms of attofarads, 0.5 attofarads. Now, they have actually done an experiment on this, and they have taken the length to be 10 micrometers, and the spacing, they have changed from 26 nanometers to up to 0.1 nanometer, and they found that the capacitance, it goes on increasing. As you decrease Z, the capacitance goes on increasing. Here, this graph shows you the energy which is stored there in the capacitor. This is the variation. Similarly, coming to the resistance, suppose I take silicon here and see what this is standard expression for the resistance of a wire, length, width, and so on. Now I go on changing the dimensions, length and width, and you can see as I go from the bulk where the resistance is 34 mega ohm meter. If I go to nanometer, here I've changed the dimensions. Okay, this is made nanometer. There, the resistance goes to exa. The prefix is exa, 10 is to 18. Okay, 10 is to 18. Now, this is for silicon. These were the parameters used. And for gallium arsenide, it comes to 0.5 pico ohm meter. Pico is 10 is to 15. So now, suppose I go to the resistor. This is a wire, and you know that the resistance, it depends upon the length and the width, and this is the usual formula that is used. Now, if I convert this into conductance, this is what is found. Conductance is here, and this depends upon the width and the length. So this conductance as a function of width goes on increasing linearly. This is what you see in your, what you can say, bulk materials. the ones which we do in the laboratories. But now, if I go to nanowires, for example, instead of the bulk wire, if I go to nanowires, you will see that the conductance varies in discrete steps. That means the conductance is quantized. So this is done both in the presence of magnetic field and in the absence of magnetic field and in the presence of magnetic field. So you can see the quantization very clearly. So this is 2 e square by h, this is twice that, and this is 3 times that. So if you measure the conductance as a function of the gate voltage, you'll see clearly the conductance steps. Now, if you apply a magnetic field, this quantization is increased. That means more quantization takes place, and you can see the steps now. But the steps, they are not at 2 e square by h, they are at e square by h. That is, this is half of this. And here again, you can see one more step at 1.5 and so on. So there is quantization. Okay, just because of the structure and because of the magnetic field in addition. Okay, now suppose I take this is also a kind of a nano channel, nano wire like. So here the structure is slightly different. You have two gates here, and you have the electrons able to move through this. And here also the conductance is quantized. Okay, conductance as a function of width of this channel. Now, if you measure the ratio of h upon e square, that is these ratios, you will find that it is to 25,812 ohms. Okay, this is called as a von Klitzing resistance. Nowadays, this has become a standard of resistance. Okay. Now, very recently, because of this standard, they have done away with our old system of units. That is, we had those units for length, mass, time, and so on. Nowadays, they depend upon what are called as definitions based on constants of nature. The definition of kilogram is not going to be there. Earlier, the kilogram was meant as a platinum iridium alloy cylinder stored in Paris. That was the mass of that, and that was the standard. But nowadays, we are not going to do that. It is not being done since 2019. Now, these are the different symbols which are going to be used. That means the parameters. You can see the frequency. Okay. Then you have the velocity of light, h, and so on. These are all constants of nature. These will be the system of units. So it is changed now. Now, this I discussed about the point contact. Now, if this is actual measurements, you can see the conductance. It has got these steps. Now, so gold, which I've already mentioned, you go on cutting it into smaller and smaller pieces, you get red color quantum dots of. Now, if you change the sizes, the colors will change. But now this can be done in a different way also. Suppose I take cadmium selenide quantum dots, and if I change the size, as I've shown you just now, the colors change. You can do it in a different way. Suppose I take a ternary alloy of cadmium selenide tellurium, and if I find the keep the size same. Here I'm keeping the size to be 5 nanometers, and you'll see that by just changing the alloy, here it is a binary alloy, cadmium telluride, and this is cadmium selenide. You can see that the colors are not the same, they are different. So by changing the composition of the quantum dot, you can change the color. So this gives you another freedom of changing the colors, of getting the colors. Okay, let me go down to the applications. Sorry, I'm taking more time, sir.
No, but very interesting.
I'm just go quickly through this. Applications, you can find them in medicine, in drug delivery system, targeting laser crystals, and even regenerating nanofibers of the spinal nerves. Then in medicine, you have what are called as the nanobots. These are the nanobots which you have And you can see this. And each nanobot, you remember, should have a sensor, electrodes, catalysts, actuators, and all that. All of them is in this tiny nanobot, which can go into your body and do whatever job it has been assigned. You can have applications in energy for solar panels, batteries, then in automotive fields, like you can have fuel additives, fuel cells, catalytic converters, and so on. Then in electronics, we have OLEDs, TVs, phones. I can give many examples. These are only small, a few of them, which I have listed here. Textile additives, which I showed, you can have anti-wrinkling, then antibacterial, and so on. Then in food security, you can have nanosensors, which can detect the contaminants in food. As I said, in sports, you have got lightweight carbon frame, tennis rackets, you have cycles, and so on. And nano can help in environment. You can have nanostructured filters, which can remove the virus cells, impurities from water. You can afford drinking water, and so on. There are many applications like this. Okay, this is just an example which shows a nerve cell, and then you have silicon wires here, nanowires. And you can see how the silicon wires, they adjust themselves on this nerve. So you can use this, and then you can control the movement of the nerves. Then this is for solar light. If you shine light here, that is, if sunlight falls on this, it can get energized. Then this is another one. Here you can see there's nanotechnology can be fashionable. So you have jackets here, and then this is a dress. Dress is made up of silver, and this is made of palladium nanoparticles. They are used actually as antibacterial and anti-purifying qualities. But the purposes may be different for a fashion designer and a fiber scientist. Okay. You can have a nano paint for the cars, which is scratch proof, which is dirt repellent, and which can get brighter colors. Then you can do the same thing for the buildings also. The buildings can be used as air purifiers if you coat them with titanium dioxide. So it can reduce the pollution. Now, for students, you have different, what is it? You have the prospects. Nowadays, people have been using it for low-dimensional materials. These are transistors. Then it has been used even for quantum computing, but then it is going to be used even for neuromorphic computing also, as well as neural surfaces. So this is just to give prospects. Now, nanotechnology is revolutionizing semiconductor industry. It has improved the performance of chips and so on. If you remember, nowadays they are thinking about 2 nanometer size processor chips. There is a competition here also. But now in India also, they are developing this. So the market is going to increase. This is a projection. This was in 2024 and this is in 2034. And they are going to make almost around $115 billion by 2034. So there is a market for this nanomaterials, nanostructures. Then, of course, you have to keep in mind Moore's law. The Moore's law is increasing, but now the increase in the line, or what I'm talking about the line is, it is about the density of the transistors which are on a chip with the years. As the time goes on increasing, now we are somewhere around 25. You can see that it is slowly becoming not exponential, it is flattening. So nanotechnology is there. There is a nanoscience and technology initiative was developed by the government of India. Nano mission also was there, and then and Professor Rao was responsible for all that. Okay, these are the things which have been established. CNRO is established Institute of Nanoscience and Technology in Mohali. It's a national institute. Then in coming to Karnataka, we have the Karnataka Science and Technology, which promotes nanoscience and nanotechnology in higher education. So, and then of course you have the yearly nanotech event, that's the Bangalore India Nano, where it brings together the research industry, government, and the academy. Okay, let me skip this. At this one point, I can say recently the Union Minister has announced that India's first semiconductor chips built on 28 nanometers. Earlier, I was talking about 2 nanometers. India is now going in for 28 nanometers, and it's getting into the race of the semiconductor processing chips. Okay, education for the students, being interdisciplinary, the student has to know for all the subjects. That is not just physics or chemistry or biology. You should have a wider range of knowledge. So even if a person is doing his, let us say, BSc in biology, if he is interested in physics also, this new national education policy can provide some curated problems, academic programs, where it can be multidisciplinary, where the student learns to accept the basic concepts. Okay, so this is what is available. I think these are the courses which are there, offers in different universities in nanoscience and technology. There are opportunities in different fields, electronics, this for the students, opportunities, forensic, biotechnology, food science, control, all this using nanotechnology. So you can have jobs as application engineer, then a manufacturing engineer, technical program manager, research, of course, is there. So, but everyone should remember that there are certain concerns regarding nanotechnology. Just with respect to health, people may say you go on reducing the size, you manufacture nanoparticles, but are they good for the biological systems? If they enter the biological systems, then of course, what will be the effect? Many people are worried about the effect of this on the health. Can these nanoparticles lead to genetic damage? What about the long-term exposure to nanoparticles? Here, I would also like to mention that recently there's been talk about the plastics, nanoplastics. So a great deal of research, or you can say study, has to be done so that we can measure or we can diagnose, we can see what is the effect of these plastics on the human body and take accordingly whatever steps are needed. The environment also can get affected. As I said, there are palladium and silver nanoparticles which can be used on the buildings, which can be used as antibacterial. But what about other nanoparticles? What about water, soil? If they enter the soil, what happens? What happens to the agriculture, growth of the plants? So then ethical. Now, do free nanoparticles pose any potential risk? Again, the same thing. Then with the emergence of AI, these implications of nanoproducts need to be properly understood. So AI can be of use for us because it has got a lot of data which is available and done till so far, and it can tell us what strategies and regulations can be done so that better life and sustainability can be effected. So technology will continue to change the world. We should all make sure that it changes for the better. Okay, so that is with that I'm going to close. Now, this is the illusion of control. This is just a comic strip which I'm showing. So here you can see a boy giving water to the plants. And then he says, it is up to me. I can control how much water I want. I can give it to you and you can grow. So without me, you're as good as dead. But you can't say what nature has to do. That means your control is illusionary. So we have to think about all this, and then we have to deal with the nanoparticles. Okay, I close with these quotes from great books: ignite imagination. Imagination leads to creativity. Creativity blossoms thinking, and thinking provides knowledge. Knowledge makes you great. So these are the things which students should know. So thinking is progress. Non what actions are excellent? to gladden the heart of a human being, to feed the hungry, and to remove the wrongs of the injured. So finally, with this, I close with a quotation from the Nobel laureate, as I told Bucky Balls, be a scientist, save the world. So that is the final takeaway. So after all, it's the world, it's our world, and we have to think about the future of the next generation. So thank you, everyone. Thank you for your patient hearing.
Thank you very much. Very informative and very exciting talk.